Statistical methods. One announcement is that it's really important that you do attend. It is really important that you do attend your lectures and your example class every week, right? Okay, you listen to me, guys. It is really important. Otherwise, I may write to your parents and complain about you guys. I'm just kidding. But, okay. All right. Now, yesterday, after the class yesterday, I uploaded the handwritten notes and the videos for the sessions. Unfortunately, the videos for the example classes did not appear. I don't know why, because I think there's some technical problems with the media services. The media services always have some problems. I think they recorded the wrong visualizer yesterday in the example classes. But the video for the lecture yesterday, I'm sure it works okay. Some of you might have seen it yesterday. The video, the podcast for the lecture is working okay, right? Anyway, hopefully this lecture will also be recorded without any trouble. So as soon as I go back to my office, I will upload the podcast for this lecture, right? The fact that I'm podcasting does not mean that you should skip the lectures. It's really important that you do come to the lectures and the example class. Okay? Right. Yesterday, I was talking about some discrete distributions. The first discrete distribution I talked about was the Bernoulli. The second one was the discrete uniform, and the third one was the binomial. Let me go through the binomial one more time. Okay, this is number 3, which is binomial. So the variable of interest for binomial is the number of successes in a sequence of m independent Bernoulli trials with parameter p. The probability mass function this is the formula for the probability mass function, or the PMF, right? The expected value of x is equal to m times p. The variance of x is m times p times 1 minus p. The moment generating function, at the end of the class yesterday, I asked you to work it out. Did you manage it or not? I asked you to work out the MGF of binomial. Well, if you haven't managed it, I will do it I will do it here right now. All right, by the definition of an MGF, right? Because binomial is a discrete random variable, you can write the MGF in this form. Okay. All right. You see what I've done? I have taken out this factor outside the summation because this does not depend on x. All right. What remains inside the summation is this. Right. Now I'm going to use a result that you might remember. If you don't remember, I will let you know in a minute what that result is. Can you tell me the result that I have used to go from this line to this line? What is this result known as, guys? It's known as the, have you seen this before, guys? The binomial expansion? Yes? No? Talk to me, guys. Well, had you seen this, something known as the binomial expansion? It goes like this. It goes, if you have something like a plus, it's not working. Sorry. It goes like this. A plus, if you have something like a plus b raised to the power n, right, it can be written in the following form. You guys seen this before or no? This result here is known as the binomial expansion. And that is precisely what I have used to go from this line to this line, right? And therefore the MGF of a binomial random variable is equal to this. Okay? Is that clear, guys? Yes? All right. Now, the next distribution, number 4, the next distribution is number 4, which is negative binomial, right? And the variable of interest, in this case is the number of independent Bernoulli trials to reach R successes. So R is an integer, P is a number between 0 and 1. Okay? Okay? And in this case, the probability mass function of a negative binomial variable is given by the following. Okay, so this is the, you guys okay? Yeah. So this is the PMF of a negative binomial random variable. The expected value is R by P. The variance is P squared. The MGF please try to do this by yourself. Okay, try to find the MGF of a negative, or try to derive the MGF of a negative binomial random variable. It's not difficult. It's similar. Well, it's a little bit more involved than the binomial case. So let's try and see if you can do it. There are other definitions. I mean, this probability mass function is only one way of defining a negative binomial distribution, right? There are other ways of defining a negative binomial distribution, right? I'll just write it down. There are at least three other ways. There are at least three other ways of defining a negative binomial random variable. But in this course, the definition I will use is this one, right? I mean, you might have seen some other definitions in some other courses you have taken in the past. But the definition I will use here is this one. Okay, guys? All right, that's number 4. Number 5, in this case, the variable of interest is the is the number of independent Bernoulli trials to reach the first success. So in other words, this is a particular case of the negative binomial variable when R is equal to 1, right? All right, it's the particular case of a negative binomial when R is 1, right? In this case, the probability mass function is this is the probability mass function. The expected value is 1 by P. The variance is this, and the MGF the MGF can be written like this. The derivation will take only a minute. I mean, all you have to do is just take the P is a constant, so pull it outside, so it becomes P. I'm going to write T as T minus 1 plus 1, X 1 minus P, X minus 1. Now I'm going to take this one outside the summation sign, so it becomes P oh, sorry, what did I do? I'm sorry, guys. I'm sorry. Sorry. I should have written like this. I meant to write X. I meant to write X as X minus 1 plus 1, right? And take this one, the second one, outside the summation sign. So this will become P E T Right, now this is your 2 years of mathematics. How do you find the sum of this term? All right, I'm going to make a substitution, say y equal to x minus 1, right? If I make this sub, right, if I make this substitution, then this sum here will go from 0 to infinity of e of t 1 minus p raised to y. Now this must be familiar to you, or sum like this must be familiar to you, which is known as the, what is it known as, guys? Yeah? This sum is known as the geometric series, right? I'm sure you have seen this before somewhere, long time ago maybe. So this is known as the, I'll write it down if you don't know, guys. You should have something like, yeah, of a to the power y, then this is 1 provided that a is less than 1. So this is the geometric, this is known as the geometric sum. The series, or the sum of a geometric series, right? Provided that a is less than 1, or the absolute value of a is less than 1, okay? So this is the MGF of a geometric random variable. Is that clear, guys? Yeah? Right. All right, let's put this over here, guys. If anything is not clear, just feel free to ask me, okay? All right, the next one, so this is number 6. Number 6 is the Poisson distribution, right? Poisson is a French mathematician. In French, I know Poisson means fish. Just like in, there's an English mathematician called Fisher. So it's similar. Anyway, the variable x in this case is the number of rare events. So, for example, accidents or floods or hurricanes or things like that can be described by a Poisson distribution, right? Okay, and the probability mass function is given by this formula, where x can take any non-negative value, right? And lambda is the only parameter which represents the average number of rare events. So given a time period, for example, 1 year or 10 years or 20 years, lambda represents the average number of rare events over that period of time. Okay? The expected value of x is lambda. The variance of x is also lambda, right? And the moment generating function of x is once again is this is the definition of a MGF for a discrete variable. Okay, and this can be written as this. Now, have you guys seen this series before? You have or have not? This series, what's it known as? Exponential, yeah. So E of lambda E t. Right, that's because using the fact that Taylor expansion for E of y is I'm sure you did this ages ago, I guess. This is known as the Taylor series expansion, or some people call it the Maclaurin series expansion for the exponential term, right? Okay. So this is what I have used to go from this line to this line. Okay. All right, guys. Right, now, so we are done with the discrete distribution, so let's move on to page 5. Page 5 is on starting with continuous distributions. All right, the first distribution I'm going to talk about is the normal distribution. I'm sure all of you have seen this before, the normal distribution. The normal distribution is perhaps the most popular distribution in statistics. And but a lot of books say that, I mean, you might have heard this before, but some people say that the normal distribution is the oldest distribution in statistics. But unfortunately, that's not correct. There are distributions proposed before the normal distribution, but that are not as well known as the normal distribution. I will talk about that later in the course. There's a distribution called the Laplace, which I talk later, which is older than the normal distribution, right? Okay, but I just wanted, this is just a historical point, yeah, that the normal distribution is not the oldest. Okay, the PDF, or the probability density function of a normal distribution, is given by this formula, right? There are two parameters to it: mu, which takes values between minus and plus infinity, and sigma, which is always positive. Yeah. And x is the domain of the distribution. The domain of the PDF is from minus to plus infinity. Okay. You should draw a graph of this function, right? It will look something like this. So this is the point mu, right? Mu is the center point. This goes to minus plus infinity. This goes to minus infinity. And this is f of x versus x, right? Okay, and in both directions, that is on the left and the right, the tail of the distribution decays to 0, but it never reaches 0. It decays to 0 smoothly, but it never reaches 0. Okay, in both directions. All right. All right, guys. So I'll put it here. Some properties of the normal distributions are the following. The first property is the expected value of a normal variable is equal to mu, right? So therefore, the mu is often known as the mean of the distribution, because the expectation is equal to mu, right? And the variance of x is sigma squared, and SD stands for standard deviation, right? Standard deviation of x, which is the square root of the variance of x, is equal to sigma, and therefore the sigma parameter is known as the sigma parameter is known as the standard deviation parameter, because SD is equal to sigma. Okay, and the MGF I proved this in the example classes yesterday. Is equal to this, right? We see the example class for proof. Okay. Some other properties are the capital F of x here. This denotes the CDF. CDF means a cumulative distribution function, right? The capital F of x for the normal distribution can be written like this, where phi is the CDF of the standard normal distribution, which is with mean equal to 0 and sigma equal to 1. Okay. By the way, I should have said at the beginning, this is the notation I shall use to denote. This is the notation for a normal random variable with mean mu and variance sigma squared. Okay. Some other properties are the following. If x1 and x2 are independent normal random variables, then ax1 plus bx2 plus c also has the normal distribution with these parameters. All right, once again, if you were in the example class yesterday, I proved this statement, right? So another property. And another property of the normal distribution is the following: that if xi are IID normal for I from 1 to n, then x bar is the sample mean, right? In other words, is 1 over n times the sum of xi, I from 1 to n, will also have a normal distribution with parameters mu and variance sigma squared by n. Again, I proved this yesterday. See sheet 0 for proof. Okay. All right. So these are some of the properties of a normal. There's a couple of more properties I need to write down. So give me a few minutes. One more property is that if if xi are IID normal, then right? This property says that if you have IID normal variables, then x bar and s squared, x bar is the sample mean, s squared is the sample variance. So let me write them down. This is the sample. This is the sample mean, and this is known as the sample variance. This is the sample mean and the sample variance are independent random variables, provided that xi are IID normal variables, right? Okay. I'm not going to give a proof of this. But I don't expect you to know the proof of this either. So, but if you can prove it by yourself, that's great. You know, but I don't expect you to know the proof of this property, only this property. Okay. There are I mean, this is an interesting historical thing because there's not just one proof. The proof of the fact that the sample mean and the sample variance are independent, there are many different proofs in the literature, right? And there are even proofs going back to as recent as last year. I mean, there's somebody from the United States, he published a proof of this result last year in a journal called the American Statistician. That's the name of the journal. So there are many different proofs of this. Some of them are short, some of them are long. So it's something you may be interested in, right? Yeah. Okay. All right, guys. Now the next thing. All right. So this is the so that's the normal distribution. The next one. So number 2. Number 2 is the log normal distribution, right? The sorry. Hi. Yeah. This what's wrong? Are you guys okay? Is the time correct? I guess the time is correct, right? So this this is the notation I shall use to denote a log normal variable. the density function. I hope I'm not being boring to you guys. I know some of this stuff is, well, so you've probably seen some of this stuff before, but I'm trying to go through this stuff as quickly as I can, right? This is the PDF, or the probability density function of the log normal distribution. And it is defined over the positive real line that x is strictly greater than 0. Mu can take any value between minus and plus infinity, and sigma must be positive. Okay. Some properties of the log normal distribution as follows. The expected value of x is given by this. Yeah. The variance of x is given by this, yeah. And one more property is, all right, the CDF. The CDF of x is given by this. Here, once again, phi denotes the CDF of n0, 1. Okay, and one other property is that if x is a log normal variable with parameters mu and sigma squared, then log of x is a normal variable with parameters mu and sigma squared. Right. Now, you might have noticed that I did not mention one of the properties. Which property I did not mention? Can you see? Huh? The MGF of a log normal variable, what do you think it will be? Huh? Come on, guys. Right? The MGF of a log normal variable does not exist. It can be proved actually that it does. I mean, how do you normally show? I know you guys probably done more math than me, but how do you normally show that something does not exist? Hmm? Contradiction? Well, contradicting what? Contradicting what? I mean, normally, if you want to show that something does not exist, you need to prove that number or that expression is equal to infinity, right? If something is equal to infinity, infinity is something that doesn't exist, right? So if you can show that, the MGF is equal to infinity, then that implies that it does not exist, right? So that's what you need to show. Try to show that the MGF of the log normal distribution does not exist. I mean, I will give you a proof next week, not this week, but in the example classes next week, I will give you a proof of this result, right? All right. Now, just bear with me. Shh. The next one is the number 3. Uniform distribution. For this, I will use the notation that X uni U and I for uniform with parameters A and B. The PDF, the density function of the uniform, is defined as this when X is between A and B, right? The corresponding CDF, by the cumulative distribution function, is defined as this. Some properties, the expected value of X is A plus B by 2. The variance of X is B minus A squared divided by 12. The mg of the moment generating function of X is given by this expression. I proved this yesterday in the example classes. So if you want to know the proof, you can look in sheet 0, right? All right, guys. So this is all for today. I will see you tomorrow if you're coming to the example classes tomorrow. Otherwise, I'll see you next week. If you have any questions about this course, feel free to send me an email or come and see me anytime you wish. If you don't have copies of the lecture notes, could you please come forward and collect one? Anybody else?
database conditions on the annex list.
Hello guys, everybody got a copy of this? You have this?
But then there seems to be another teacher.
I think you copied it wrong. I think you can see it online later on, but just a minute, let me show you. Let me show you what I wrote down. Sorry, sir. Just this is what I wrote down. But I will. Can you see it better now? So just give me a sec, sir. Sorry.
I'm so confused because there's only one east to the X here, and then there's an east for 2 and an east for 2. So I'm confused.
Yeah. What I've done here is, you see, I have written E of tx as this, E of t x minus 1 plus 1. And then I took the last second of the two ones outside, so it becomes E of t.
Right.
Sometimes we can like take a.
Could I just
Yeah, you
and
can,
it'll be online.
it will be online shortly, yeah. But you can still take a photo, yeah. Yeah, you can still take a photo. All right, see. You guys have a copy of the notes?
Yeah.
Yeah, okay, good.